Hello, and welcome to Science with Mr. Morgan. In today's episode, we are going to talk about physical properties of matter, the second part. Today, we're going to take a look at mixtures. What is a mixture? It's a combination of two or more substances in any proportions. In the chemical properties of matter episode, we're going to talk about compounds. It's important to note that mixtures are different than a compound because they are not in fixed proportions and they do not combine substances chemically to form a new substance. Instead, mixtures intermingle and keep their original properties. Now, mixtures themselves can be homogeneous or heterogeneous. Homogeneous mixtures are mixtures that have the same composition throughout the entire thing. Common examples of this include salt water, lemonade, or even hot cocoa. Heterogeneous mixtures, on the other hand, are mixtures that vary in their composition, aka they're different throughout. Now, common examples of this include oil-based salad dressings or sedimentary rocks. Mixtures can be separated by type, and this type is based on particle size. One type of mixture is a solution, and solutions are homogeneous mixtures with tiny particles. These particles are too small to see and too small to settle or be filtered out. Another type of mixture is a colloid. These are homogeneous mixtures with medium-sized particles. These particles are large enough, however, to see, but they are not large enough to settle or be filtered out of the mixture. And the last type of mixture we're going to touch on are suspensions. Suspensions are heterogeneous mixtures with large particles. These particles are large enough to see and large enough to settle or be filtered out. Now, since mixtures are physical and not chemical, they can be separated. This can be done through things like boiling, dissolving, or filtering the mixtures, like we were just talking about with filtering. Sometimes they are used individually, and other times they're used in unison with one another. So imagine we have a bucket of water and a pile of sand mixed with sugar. Sand and sugar in this hand, water in this hand. We want to separate the mixture of sand and sugar into individual components. So we want to separate it into sand and sugar. How do we do that? I mean, one way we could individually pick out the tiny particles of sand and the tiny particles of sugar, but that would take forever. Instead, let's use the bucket of water. To start, we're going to mix the water with the sugar and the sand. The sugar is going to dissolve in the water, but the sand will not. Once we are sure that the sugar is totally dissolved, the sand can be filtered out. And this can be done by running it through a filter that the water will seep through, but the sand particles are too big to fit through. After this, we will have the sand alone by itself, mostly, and the sugar water in our separate containers. Once the sugar water is separated from the sand, the sugar water can then be boiled. Boiling will cause the liquid to evaporate, but the sugar will remain. So in the end, we will have a container of sugar and a container of sand, and the water will have evaporated into water vapor and be dispersed throughout. Now that we've spent quite a bit of time talking about mixtures, let's look at a question. Which of the following is not an example of a homogeneous mixture? Remember, homogeneous is same throughout. Salt water, lemonade, oil-based salad dressing, or hot cocoa. Again, remember, homogeneous mixtures are the same throughout. Salt water, lemonade, and hot cocoa are all homogeneous mixtures, assuming that they're fully mixed and you didn't leave a little powder at the bottom. Heterogeneous mixtures are not the same throughout. An oil-based salad dressing is a heterogeneous mixture. So the correct answer there is oil-based salad dressing. Anyways, that's enough about mixtures. Instead, let's talk about some laws. And these are scientific laws that I'm talking about. The first one we're going to talk about is the law of conservation of mass. This law states that matter cannot be created or destroyed, which is similar to the law of conservation of energy. That law states that energy cannot be created or destroyed. Mr. Morgan, if matter can't be destroyed, what about things like when something burns? Where does that matter go? Good question. Burning and other changes in matter do not destroy the matter. The mass is always the same before and after the changes occur. It just gets transferred into a different form. The next law that we're going to talk about is Boyle's law. This law states that if the temperature of a gas is held constant, Decreasing the volume of the gas increases its pressure. The same happens in reverse too. If you increase the volume of the gas, the pressure will decrease. And this is an inverse relationship. But what does that mean? All an inverse relationship means is that as one part goes up, the other part goes down. In this case, it's volume of a gas and pressure. And Boyle's law has a formula that can be applied to it. The formula is P1V1 equals P2V2. And this is the shorthand way of saying the initial pressure, or the first pressure, aka P1, times the initial volume, or first volume, aka V1, is equal to the final pressure, or second pressure, aka P2, times the final volume, or second volume, aka V2. Let's do a practice problem. We have a sample of argon gas that has an initial pressure of 10 atm and an unknown volume. This sample has a final pressure of 100 atm and a volume of 20 milliliters. How do we figure out what the initial volume is? First, let's identify what each of these numbers are. P1, the initial pressure, is 10 atm, atmospheric pressure. V1 is the initial volume, but it's unknown, so we'll call it V. P2, the final pressure, is 100 atm, and V2, the final volume, is 20 ml. Now that we know what is what, we can just plug it into our formula. Remember, the formula is P1V1, initial pressure times initial volume, equals P2V2, final pressure times final volume. This means that we have 10 atm times V equal to 100 atm times 20 milliliters. To start, let's take the two known numbers, the 100 and the 20, and multiply them together. 100 times 20 is equal to 2,000. Now we have 10 times V equals 2,000. To get the V alone, we divide both sides by 10 because it's opposite of multiplication, 10 times V, so we divide, and what we do to one side we do to the other. So we have 2,000 divided by 10, which ultimately equals 200. So our initial volume is equal to 200 milliliters. And if we want to check our work, we could take 10 atm times 200 milliliters equal to 100 atm times 20 ml. 10 times 200 is equal to 2,000, and 100 times 20 is equal to 2,000. So we have 2,000 is equal to 2,000. Long story short, our initial volume is 200 milliliters. And that brings us to the end of today's lesson. Until next time.